Something is wrong with the beginning of the universe, not later, not billions of years after it formed, but right at the start. For a long time, cosmology relied on a quiet assumption that the universe began in a simple state, almost smooth, almost uniform, with very little structure. Complexity, according to this view, was supposed to arrive later, after expansion, after cooling, after tiny differences slowly grew into larger ones over enormous stretches of time. It was a story that felt stable, predictable, and safe. But the newest observations are breaking that story. When we look deep into the early universe now, we are not seeing simplicity. We are seeing organization, not faint hints of structure or subtle irregularities, but systems that already look arranged, and they appear far too early. According to everything we expected, this should not be possible. The early universe was supposed to be limited by heat, limited by density, limited by time. Matter needed time to gather. Gravity needed time to amplify small differences. Energy needed time to disperse. Yet, the structures we are detecting do not look like they waited. They look like they arrived almost immediately. This creates a problem that is easy to underestimate at first, because it is not about one strange result or one unexpected object. It is about a pattern, again and again. As observations push closer to the beginning, the same result appears. Organization shows up too early. Complexity emerges before the timeline allows for it, and the data itself is not chaotic. That is the unsettling part. It is consistent. Different measurements, different regions, different techniques, all pointing in the same direction. The universe did not ease its way into structure the way we thought it did. That consistency forces a quiet but serious question. If complexity appears almost immediately, then what was the universe doing before that? The standard story depends on a long stretch of simplicity at the beginning. That simple phase is not optional. It is the foundation. Without it, the timeline we use to explain everything else begins to weaken. Early galaxies, early stars, early chemical organization, all of it assumes there was enough time for gradual assembly. But the observations are compressing that time. They are removing the buffer. And once that buffer disappears, the entire sequence becomes unstable. This is not a dramatic crisis. There is no single discovery that shatters everything at once. Instead, there is a slow accumulation of discomfort. Each new observation fits cleanly with the others, and each one makes the same assumption harder to defend. That assumption is simplicity. We never directly observed a simple beginning. We inferred it. We assumed it because earlier instruments could not see far enough back, because smooth beginnings made the equations manageable, and because gradual development felt natural. Now we can see deeper, and what we see does not look simple. It looks structured, not finished. not mature, but undeniably organized. This does not mean the equations stopped working. They still describe expansion, cooling, and basic interactions extremely well. What is breaking is the story we built around them, the idea that complexity must wait. If that idea fails, then the universe's history may not be a slow climb from simplicity to order. It may have begun already complex. And that possibility changes how we interpret everything that comes after. Because once you question the beginning, nothing downstream remains untouched. So before we talk about galaxies, before we talk about stars, before we talk about planets, we have to step back. We have to ask why gradual formation became the default expectation in the first place, and what it means if the universe never followed that path at all. That is where the real tension begins. Before going any deeper, if you're drawn to questions about how the universe really works beneath the surface, take a second to like the video, subscribe, and share it with someone who enjoys thinking about these things too. What comes next only works if you're willing to sit with uncertainty for a while. Right now, picture a quiet hotel room late at night. The lights are low. Outside the window, the city has mostly gone silent. Tomorrow, there will be a conference, a room full of colleagues, slides ready to be shown, equations prepared, and conclusions expected. But tonight, something doesn't feel settled. The data has been reviewed again and again. The numbers haven't changed. The measurements are solid. The uncertainties well understood. There's no obvious mistake to fix, and no simple adjustment to make. What's uncomfortable isn't the data itself, but what the data refuses to do. It refuses to fit the story it was supposed to belong to. This is the moment before public explanation, before everything gets wrapped in careful language and formal presentation. Once the results are shared, they will sound controlled, cautious, and technical. But right now, alone with the slides, the tension is harder to ignore. The beginning of the universe was supposed to be simple. That expectation is embedded in every model, every simulation, every timeline used to explain how matter turns into structure. And yet, the earliest observations don't reflect that simplicity. They reflect organization. This realization doesn't arrive with drama. It arrives quietly, through repetition, through consistency, through the absence of errors that could explain it away. There's a subtle pressure that builds when results keep agreeing in the wrong direction. At that point, the questions begin to change. It stops being about where something went wrong and starts becoming about why something else was expected in the first place. That shift is uncomfortable because expectations don't come from nowhere. They are inherited, reinforced over decades of theory and observation, strengthened by success in other areas. The gradual picture of the universe worked extremely well for a long time. It explained expansion, cooling, and large-scale patterns. It became familiar, even comfortable. So, when new observations refused to follow that pattern, The instinct is not to abandon the framework, but to protect it. To assume there must be a missing step, a calibration issue, or a temporary mismatch. But there comes a point where protecting the framework feels less honest than questioning it. And that is where this moment sits. Late at night, slides open. Cursor blinking. No audience yet. Just the quiet recognition that something foundational may need to be re-examined. This is not about making bold claims or announcing a revolution. It is about acknowledging tension before it gets smoothed over. Because once the presentation begins, the language will soften, the uncertainty will be carefully bounded, and the discomfort will be framed as ongoing work. But before all of that, there is this pause, this threshold. Not a conclusion, not a solution, but a moment of reflection. Before we try to explain anything away, we have to remind ourselves what we originally expected to see when we looked back toward the beginning of the universe. We need to understand what assumptions shaped that expectation, and why those assumptions felt so reasonable for so long. Only then does it make sense to ask what it means when the universe does not follow that script. For most of modern cosmology, the idea of a gradual universe did not appear suddenly, nor was it imposed without reason. It emerged slowly from a combination of observational limits, theoretical needs, and a desire for internal consistency. When scientists first began constructing serious models of the universe's origin, they faced a fundamental challenge. The early universe was an extreme environment, far beyond anything that could be recreated or directly tested. To make progress, they needed assumptions that were not only physically reasonable, but also mathematically controllable. A simple beginning satisfied both requirements. In the earliest moments after the Big Bang, conditions were believed to be extraordinarily uniform. Temperatures were extremely high, densities were immense, and matter existed in forms governed by basic interactions rather than complex structures. Under such conditions, it seemed unlikely that intricate organization could exist. The dominant forces would act almost evenly across space, smoothing out differences rather than amplifying them. Any irregularities present at that stage were expected to be extremely small, subtle variations, rather than pronounced features. From this perspective, complexity did not just seem absent, it appeared physically discouraged. This expectation of simplicity was reinforced by what early observations could reveal. When astronomers examined the universe on the largest scales, they found a remarkable degree of uniformity. Matter was distributed in broad patterns that looked consistent from one region to another. Differences existed, but they were modest and statistically predictable. These observations supported the idea that the universe began in a relatively smooth state, with only slight variations that would later grow under the influence of gravity. The mathematics also favored this view. Equations describing the expansion of the universe, the behavior of matter and radiation, and the evolution of density fluctuations all behaved more cleanly when initial conditions were simple. A smooth starting point allowed scientists to trace how tiny differences could slowly increase over time, eventually leading to the large-scale structures observed today. Without that simplicity, the equations became far harder to interpret, and predictions became unstable. In this sense, simplicity at the beginning was not just a physical assumption, but a practical necessity. As cosmological models improved, this gradual picture continued to hold up. Simulations showed that small difference in density could indeed grow over billions of years, forming the filaments, clusters, and large-scale patterns that surveys were beginning to map. These results did not require sudden jumps or unexplained accelerations. Everything unfolded step by step, governed by known forces operating over long periods. The universe, according to these models, behaved patiently. This reinforced the idea that time was a critical ingredient. Structures did not appear quickly because they could not. Matter needed time to cool, to slow down, and to respond to gravitational attraction. Gravity itself, while powerful, operates gradually on large scales. It amplifies small differences, but it does so over immense spans of time. The slow emergence of complexity was therefore not just expected, it was built into the logic of the physical processes involved. Because of this, the assumption of a simple beginning felt not only reasonable, but almost unavoidable. It fit the data available at the time. It fit the mathematics, and it fit the physical intuition scientists had about how systems behave under extreme conditions. There was no strong incentive to question it, because nothing clearly contradicted it. Over time, this assumption became deeply ingrained. It was no longer treated as a provisional idea, but as a starting condition that could be taken for granted. New theories were built on top of it. New simulations assumed it from the outset. Even debates within cosmology tended to focus on details that occurred long after the beginning, rather than on the nature of the beginning itself. This gradual framework also provided a sense of order. It allowed scientists to divide cosmic history into distinct phases, each following logically from the last. There was an early phase dominated by radiation, followed by a matter-dominated era, and much later, the formation of stars and galaxies. Each phase had a clear place in the timeline, and each depended on the assumption that earlier phases were relatively simple. That structure was reassuring. It suggested that complexity had a clear origin and a clear explanation. Nothing needed to appear prematurely. Nothing needed to violate the expected sequence. Given enough time, the universe could naturally evolve from simplicity to complexity without contradiction. For decades, this picture remained largely unchallenged, not because it was proven beyond doubt, but because the tools required to test it directly did not exist. Observations of the early universe were limited in resolution and depth. Scientists could see broad patterns, but not fine detail. The absence of visible complexity was interpreted as confirmation of simplicity. even though it was also consistent with observational limits. In that context, the gradual universe assumption felt safe. It rested on solid reasoning, matched available evidence, and provided a coherent narrative for cosmic evolution. It became the foundation upon which much of modern cosmology was constructed. But that safety depended on one critical condition: that the earliest stages of the universe remained largely beyond direct scrutiny. As long as those stages could only be inferred indirectly, the assumption of simplicity could persist without serious challenge. Once observations began to push closer to the beginning with greater precision, that assumption would no longer be protected. And it is precisely that shift, from inference to direct observation, that begins to erode the intellectual comfort this framework once provided, opening the door to the first genuine contradictions. Once the assumption of a simple beginning took hold, it did not remain isolated. It spread quietly into nearly every part of cosmological thinking, shaping not just individual theories, but the entire way scientists organized cosmic history. Over time, gradual formation stopped being one idea among many and became the framework within which all other ideas were evaluated. Models of how structure forms depended on it. Numerical simulations were designed around it. Even the basic vocabulary used to describe the universe assumed it implicitly. Cosmic history came to be understood as a sequence of stages, each unfolding from the one before it. First came expansion and cooling, as the universe transitioned from an extremely hot, dense state into something more stable. Then came the formation of the simplest particles, followed by atoms as conditions allowed electrons and nuclei to bind together. Only much later did stars begin to form, and later still, galaxies. Each stage occupied a well-defined place on the timeline, separated by enormous spans of time that allowed processes to unfold gradually. Within this picture, complexity was always something that emerged, never something that existed at the start. Structure was framed as a product of patience. Given enough time, small differences would grow larger. Given enough cooling, matter would organize itself into increasingly elaborate arrangements. Nothing needed to happen quickly. In fact, speed itself became a signal that something was wrong. If a process appeared too early or progressed too fast, it was treated with suspicion. This gradual framework proved extraordinarily effective. When astronomers mapped the distribution of galaxies across the sky, the results matched predictions derived from slow growth models. Galaxies were not scattered randomly, but arranged in large-scale patterns that could be reproduced by simulations starting from simple initial conditions. Filaments, clusters, and vast, empty regions emerged naturally when gravity was allowed to act over billions of years. The universe appeared to follow the rules. The same framework helped explain why distant regions of the universe look statistically similar to one another. On the largest scales, matter appears evenly distributed, with no preferred direction or special location. This uniformity fit comfortably with the idea of a smooth beginning. If the universe started nearly uniform, then large-scale uniformity, billions of years later, made sense. Deviations would exist, but only as the result of slow, predictable amplification. Even subtle features of cosmic structure reinforced confidence in the gradual picture. The distribution of galaxy sizes, the relationship between mass and environment, and the way matter clusters on different scales could all be described using models that assumed slow evolution from simple beginnings. Each successful prediction strengthened the sense that the framework was not just useful, but fundamentally correct. As a result, the gradual universe assumption became deeply internalized. It stopped being treated as an idea that required constant justification, and instead became a background condition. New theories were developed with the assumption already built in. Researchers rarely paused to question it, not because they were careless, but because there seemed to be no reason to. The framework worked, and it worked consistently. This is how assumptions gain power in science. They do not dominate because they are declared unquestionable, but because they continue to succeed. Each successful application reduces the motivation to revisit foundational premises. Over time, questioning them can even feel unnecessary or unproductive, especially when more immediate problems demand attention. The gradual picture also offered a sense of coherence. It allowed cosmology to present a single, continuous narrative from the earliest moments to the present day. The same basic principles governed the entire story. Physical laws did not need to change abruptly. There were no unexplained jumps in complexity. Everything followed from what came before in an orderly way. That coherence mattered. It gave cosmology explanatory power not just over isolated phenomena, but over the universe as a whole. It allowed scientists to connect observations across vast distances and timescales, confident that the same underlying processes were at work everywhere. The universe felt intelligible, even if not fully understood. There was also a practical dimension to this trust. Simulations of cosmic evolution require assumptions about initial conditions. Starting from a simple state made those simulations feasible. It reduced the number of variables and allowed researchers to focus on how known forces shaped structure over time. Without that simplicity, computational models would have become far more complex and far less predictive. In this way, gradual formation was not just a conceptual preference, but a functional necessity. It made large-scale modeling possible at all. Entire research programs depended on it. Careers were built within its framework. Results were compared against its predictions. It became the reference point against which new data was judged. As generations of scientists were trained within this paradigm, it became part of how cosmology was taught and learned. Students absorbed the gradual timeline as a starting point, not as an open question. Textbooks presented it as the standard picture. Lectures framed deviations as refinements, not as challenges to the foundation itself. At this stage, the gradual universe was no longer treated as a hypothesis in the ordinary sense. It was the default assumption, something you work from, not something you work to prove. Alternative possibilities were not ignored, but they occupied the margins. They were discussed cautiously, often framed as speculative or incomplete. This did not mean the field was closed-minded. Cosmology continued to debate many aspects of cosmic evolution, from the nature of dark matter to the behavior of dark energy. But those debates unfolded within the same broad framework. They did not usually question whether complexity might appear early or whether simplicity at the beginning was truly necessary. The strength of the gradual model lay in its track record. It explained too much, too well, for too long to be casually discarded. Its success created a kind of inertia. Moving away from it would require not just new ideas, but strong evidence that the old framework was failing in a fundamental way. For a long time, that evidence did not exist, or at least did not appear to. Observations of the early universe remained limited. The earliest stages were still largely inferred rather than directly seen. Without clear contradictions, the gradual picture remained secure. And that security shaped expectations. When scientists looked toward the beginning of the universe, they expected simplicity because the framework demanded it. They expected slow growth because every successful model had taught them to. That is why the gradual universe assumption became so deeply rooted. It was not imposed dogmatically. It earned its position through repeated success. It became the backbone of cosmology, precisely because it seemed to hold everything else together. But backbones can become points of vulnerability when the structures they support begin to change. And as observations start to probe earlier times with greater clarity, the very assumption that once unified cosmology is now being placed under a different kind of pressure, one it was never designed to withstand. There was another reason the gradual picture felt so convincing, and it had little to do with equations or observations. It aligned closely with human intuition. We are naturally comfortable with processes that unfold slowly. We understand growth as something that takes time. We expect accumulation to happen step by step. Cause comes first, effect follows later. A universe that builds complexity gradually fits easily into that mental framework. An immediately complex universe does not. It feels abrupt, unprepared, difficult to reason about. When complexity appears too early, it challenges our sense of sequence. It becomes harder to say what caused what, and in what order. Gradual formation, by contrast, offers a clean narrative. It allows us to trace outcomes back to origins in a linear way. That linearity is not just convenient, it is deeply reassuring. This intuitive appeal mattered more than scientists often acknowledge. Cosmology deals with scales far removed from everyday experience, but the way theories are evaluated still relies on human judgment. A gradual universe feels plausible because it mirrors how we see complexity emerge in other contexts. systems evolve. Structures take time to form. Order grows out of simpler beginnings. That pattern appears everywhere we look in nature, so it felt natural to extend it to the universe itself. Gradual formation also introduced clear boundaries into cosmic history. It allowed scientists to divide the universe into eras with well-defined characteristics. There was a time when certain processes were possible, and a time when they were not. Some events required more cooling. Others required more matter to accumulate. Still others required previous generations of structure to exist first. Those boundaries were extremely useful. They allowed researchers to say with confidence that certain phenomena could not have occurred yet. If something appeared too early, it could be ruled out without hesitation. Time became a powerful organizing principle. It provided constraints that made predictions possible and helped distinguish between plausible and implausible scenarios. In this way, the gradual model gave cosmology structure, not just physically, but conceptually. It imposed order on an otherwise overwhelming history. Instead of a continuous blur of change, cosmic evolution could be described as a sequence of stages, each with its own rules and expectations. That made the universe easier to think about, even when the underlying physics was complex. Equally important was the role simplicity played at the beginning of this sequence. A simple starting point acted as a stabilizing anchor. If the universe began with minimal structure, then every instance of complexity later on had a clear explanation. It emerged because time allowed it to emerge. Nothing needed to appear suddenly. Nothing needed to arrive without preparation. This eliminated a whole class of uncomfortable questions. There was no need to explain why something complex appeared early, because it wasn't supposed to. There was no need to invoke unusual mechanisms or special conditions. The slow passage of time was enough. Complexity became an expected outcome rather than a puzzle. That expectation created a sense of reliability. It suggested that the universe followed understandable rules, even if those rules were expressed through complicated mathematics. It implied that any apparent mystery could eventually be resolved by looking further back along the timeline or by improving measurements. The system felt closed in the best possible way. Everything had a place. This sense of order translated into intellectual comfort. Scientists could work within the framework with confidence that they were not missing something fundamental. When predictions failed, the failures were usually local. They pointed to missing details, not to flaws in the overall picture. The framework itself remained intact. Over time, this confidence became self-reinforcing. Each successful prediction strengthened trust in the underlying assumptions. Each observation that fit the gradual model made it feel more inevitable. The idea that the universe might have behaved very differently at the beginning felt increasingly remote. That confidence was not misplaced, at least for a long time. The gradual framework delivered real results. It allowed cosmology to mature into a precise, quantitative science. It connected theory with observation across vast scales. It helped explain why the universe looks the way it does today. Importantly, it also set expectations about the future of discovery. There was a shared belief that as instruments improved, they would fill in missing details without overturning the basic structure of the story. Better data would refine timelines, adjust parameters, and resolve ambiguities, but the overall sequence would remain recognizable. In that sense, the gradual universe assumption functioned as a promise. It promised that the universe was ultimately understandable, that complexity, no matter how overwhelming it appeared, had a clear origin in simplicity, that nothing fundamentally surprising waited at the beginning. For decades, that promise held. Observations of the cosmic microwave background reinforced the idea of an early universe that was remarkably uniform. Large-scale surveys continued to match predictions derived from gradual growth. Deviations existed, but they could be explained without abandoning the framework. The universe behaved as expected, within reasonable limits. Because of this, simplicity at the beginning stopped being something that needed justification. It became something that felt obvious. Questioning it began to feel unnecessary, even counterproductive. Research attention shifted elsewhere, toward phenomena that could be studied directly and measured precisely. The comfort provided by the gradual model was subtle but powerful. It reduced anxiety about the unknown. It allowed scientists to focus on specific problems without worrying that the foundation beneath them might shift. It created a sense that cosmology, while incomplete, was on a stable path toward deeper understanding. That comfort also influenced how uncertainty was handled. When something did not quite fit, it was treated as a temporary anomaly, an issue to be resolved with more data or improved modeling. Rarely did it prompt a re-evaluation of the earliest assumptions. The beginning of the universe remained conceptually distant, safely abstract, and largely untouched. In retrospect, this comfort came with a cost. By making the framework feel secure, it discouraged active testing of its most basic premises. Simplicity at the beginning was not wrong by default, but it was rarely challenged directly. It became part of the intellectual landscape rather than an object of scrutiny. And as long as observations could not reach far enough back in time to test it, that arrangement seemed reasonable. The assumption caused no obvious harm. It supported decades of productive research. It helped build a coherent picture of cosmic evolution. For a long time, the confidence it inspired was justified. But intellectual comfort has a fragile side. It depends on conditions remaining stable. It depends on assumptions staying out of reach of direct confrontation. Once new observations begin to probe regions where those assumptions apply most strongly, comfort can turn into vulnerability. And that is the position cosmology now finds itself approaching. The gradual picture did not fail because it was careless or naive. It succeeded because it made sense, worked well, and felt right. But as the boundary between inference and observation begins to shift, The very qualities that made it comfortable also make it difficult to adjust, because letting go of an assumption that provided order, clarity, and reassurance is far harder than questioning a minor detail. And that is why the erosion of comfort matters. It is not dramatic. It is not sudden. But it signals that something once taken for granted is about to be tested in a way it never was before. The question is no longer whether the gradual model was reasonable. The question is whether it was complete. But the very strength of the gradual universe assumption concealed a weakness that went largely unnoticed for a long time. Because the idea worked so well, and because so much of cosmology depended on it, surprisingly little effort was devoted to testing whether it was actually true in a direct sense. Simplicity at the beginning was not something scientists could observe outright. Instead, it was inferred from models, extrapolated backward from later conditions, and reinforced by the absence of data that suggested otherwise. This distinction matters. An inferred condition is not the same as an observed one. For decades, the early universe remained a place we could describe mathematically, but not see clearly. The smoothness attributed to it was not confirmed by detailed measurements, but assumed because nothing visible contradicted it. That assumption felt reasonable given the limits of available instruments. Early telescopes and detectors simply could not look far enough back in time with sufficient resolution. They could capture large-scale patterns, averages spread across enormous regions of space, but not fine detail. When scientists examined the earliest observable signals, they saw uniformity because they were only able to measure uniform features. Small-scale organization, if it existed, would have been invisible. In that context, the early universe appeared smooth by default. The absence of visible complexity was interpreted as evidence that complexity was not there. This was not a careless mistake. It was a practical conclusion drawn from limited information. But over time, that conclusion hardened into certainty. As long as observations remained coarse, the gradual model faced no serious challenge. The data available were consistent with it, and nothing demanded a different explanation. The assumption of simplicity did not conflict with what could be seen, so it remained intact. Its stability depended on that observational limitation, even if that dependence was not obvious at the time. The gradual model, in effect, required the earliest stages of the universe to remain partially hidden. It relied on the fact that we could not yet test its core premise directly. As long as the beginning stayed beyond detailed scrutiny, the framework remained safe. That is why the unease introduced earlier is important. It does not arise from a single surprising measurement or an isolated anomaly. It arises from a shift in capability. When observations begin to reach earlier epochs with greater clarity, the gradual assumption is no longer sheltered. It moves from being a background premise to being a testable claim. And once an assumption becomes testable, it becomes vulnerable. This vulnerability does not imply that the assumption is wrong. It means that it can no longer be taken for granted. The moment data begin to probe the era where simplicity is supposed to dominate, the model must confront evidence rather than rely on inference. That transition changes the nature of the discussion entirely. What begins to feel unstable is not the mathematics or the physical laws themselves. Those continue to describe many aspects of the universe with remarkable accuracy. What feels unstable is the narrative built around them. The story that says complexity must wait, that structure must emerge slowly, that time alone is sufficient to explain organization. The foundation does not crack all at once. Instead, it starts to feel less firm under closer inspection. The confidence that once came from success now gives way to cautious reassessment. Not because the model has already failed, but because the conditions that once protected it are disappearing. This is an important distinction. There is no dramatic collapse here, no sudden invalidation of decades of work. What changes is the status of an idea. Simplicity at the beginning moves from assumption to question. The next step, then, is no longer theoretical. It does not come from speculative reasoning or abstract modeling. It comes directly from observation. From looking at the earliest structures the universe allows us to see, and asking whether they match the expectations set by gradual formation, this is where tension begins to build in a new way, not as a philosophical discomfort, but as an empirical one. When data begin to show features that should not exist yet, the gradual model is forced into a position it was never designed to occupy. It must explain not just what happens later, but what happens almost immediately. The fragility of the model lies here. It was never meant to handle early complexity. Its logic assumes that complexity is a late-stage outcome. When organization appears too soon, the framework does not break outright, but it struggles to respond without adding new conditions or exceptions. And that struggle is significant, because it reveals that what once felt like a secure foundation may, in fact, depend on a very specific picture of the beginning, one that was accepted largely because it could not be directly tested. As observations sharpen, that picture is no longer protected by distance or resolution. The early universe is no longer an abstract starting point. It is becoming an observable environment. And that is where the first real contradiction enters. Not as a dramatic revelation, but as a quiet mismatch between expectation and evidence. A mismatch that cannot be ignored simply because it appears early. A mismatch that signals the transition from comfort to confrontation. From this point forward, the question is no longer whether the gradual model made sense. The question is whether it can survive direct observation of the beginning itself. And this is where the tension stops being abstract. For the first time, observation reaches a period that was never meant to be complicated. This is not an era reconstructed only through equations or inferred indirectly from later effects. It is a time we can now see directly with enough resolution to move beyond broad averages and examine what actually existed, not what was assumed to exist. According to the gradual model, this moment in cosmic history should look unfinished in a very specific way. Matter should still be widely dispersed. Differences in density should be shallow and minimal. Gravity should only just be beginning to amplify those differences. Organization, if present at all, was expected to be rare, fragile, and barely detectable. Most regions should look almost the same, smooth, with only faint hints of what would come much later. That expectation was clear, and it was consistent. So when observation finally reaches this era, the test is simple. Do we see what we expected? And the answer is no. Instead of near uniformity, the observations reveal recognizable structure. Not modern galaxies and not fully mature systems, but arrangements that already display coherence. Matter is not merely scattered or clumped at random. It appears organized into forms that suggest assembly has already taken place. These are not isolated particles drifting without pattern. They are systems that show internal relationships, even at this early stage. That alone would be surprising. But the deeper issue is not what these structures look like. It is when they appear. According to the established timeline, there should not have been enough time for this to happen. Not enough time for matter to gather. Not enough time for gravity to amplify differences to this degree. And not enough time for organization to cross these thresholds. Yet the structures are there, present at moments when the gradual model says simplicity should still dominate. This is where disorientation sets in, because the contradiction is narrow and precise. The problem is not size, not brightness, and not chemical composition. It is timing. They appear too early. If the gradual picture were correct, these same structures should exist later, after long periods of growth and extended interaction, after the slow work of gravity over vast stretches of time. Instead, the universe appears to reach these milestones ahead of schedule. The clock says one thing, while observation shows another. The gap between them cannot be ignored. This does not immediately explain why it happened. It does not point to a new mechanism or reveal how organization accelerated. It only tells us that something occurred sooner than expected, and that alone is enough to create discomfort. Cosmology relies on timing as a constraint. Time is what keeps processes ordered and prevents everything from happening at once. When timing breaks down, sequence becomes unstable and explanation becomes fragile. What makes this especially unsettling is how calm the contradiction is. There is no dramatic anomaly and no extreme outlier demanding attention. The data looks clean, measured, and consistent. These structures are not ambiguous smudges or artifacts. They appear exactly where the instruments say they are, at exactly the times the models say they should not be. Because the contradiction is quiet, it becomes harder to dismiss. There is no obvious mistake to point to, and no single parameter that can absorb the discrepancy. the gradual model does not collapse here. It simply fails to line up, and that misalignment introduces a subtle but persistent unease. If structure appears earlier than expected, then the assumption that complexity must wait begins to weaken, not collapse and not disappear, but weaken. At this point, no sweeping conclusions are necessary. There is no need to rewrite cosmic history or invoke new physics. A single careful statement is enough. Organized structure exists at a time when simplicity was expected. That fact alone is sufficient to place pressure on the framework built earlier. It interrupts the sense of order that gradual formation once provided, and leads naturally to the next question. If this were a single case, it might be absorbed. One exception can be tolerated, and one anomaly can be explained away. But the story does not end here. The next observations do not return the universe to simplicity. They repeat the pattern, and that is where the discomfort begins to grow. What deepens the sense of disorientation is not just what is being observed, but how it presents itself. There is no dramatic anomaly announcing that something has gone wrong. No single object standing apart as obviously impossible. The data does not appear chaotic, noisy, or inconsistent. On the contrary, it looks measured and controlled. Different observations align cleanly. Independent analyses agree. Internally, the results make sense, and that is precisely what makes the contradiction difficult to ignore. The structures appear exactly where the gradual models say simplicity should still dominate. That is the entire problem. Not hidden in complex details, not buried in uncertain measurements. It sits plainly in the timing, and it arrives without spectacle. There is no need to exaggerate what is being seen, because the mismatch speaks for itself. If organized structure exists at a time when only near uniformity was expected, then at least one assumption about early cosmic development is incomplete. That conclusion does not require speculation. It follows directly from the comparison between expectation and observation. This creates a very specific kind of discomfort. It is not confusion about the data itself. Astronomers are not unsure of what they are seeing. The signals are clear. The measurements are repeatable. The uncertainty lies elsewhere. It lies in how these observations fit into the sequence that was supposed to explain them. The established timeline assumes that the early universe moves through stages in a particular order. First, near uniformity, then small irregularities, then gradual amplification, and only later recognizable structure. When organization appears too early, that order begins to blur. It feels as though steps are being skipped, or at least compressed far more tightly than anticipated. This compression is unsettling because the gradual model relies on separation between stages. Time is what allows one process to finish before another begins. When that separation shrinks, explanations lose clarity. Processes overlap in ways they were not meant to. The sequence that once felt orderly becomes harder to trace. At this stage, there is still no need for sweeping claims. No one is required to rewrite cosmology or propose entirely new origins for the universe. The situation does not demand radical language. The only statement that needs to be made is a careful one. Organized structure appears earlier than the gradual model allows. That single fact is enough to disturb the framework built earlier. It does not tear it down. It does not invalidate everything that came before. But it introduces tension into a structure that once felt stable. And because the contradiction is calm and precise, it becomes harder to dismiss. There is no obvious flaw to point to. No single parameter that can simply be adjusted to restore the expected order. The issue does not reside in one corner of the model. It presses against the timeline itself. Attempts to absorb the discrepancy quickly run into limits. Adjustments that might help in one area often cause problems in another. The sense grows that the framework is being asked to explain something it was not designed to handle. Not because the data is extreme, but because it is persistent. This is why the contradiction refuses to go away. It does not fade with additional analysis. It does not resolve itself when new observations are added. Instead, it remains present, quietly reshaping how the early universe must be thought about. The discomfort deepens because there is no dramatic turning point. No moment where one can say, "This is where everything changed." Instead, the realization builds slowly. Each observation reinforces the same mismatch. Each one makes it harder to believe that the issue is isolated. At this point, the question shifts naturally. If this were truly a single case, it might be absorbed without lasting consequence. Science is well equipped to handle anomalies. Unusual results often find explanations that preserve existing frameworks. But what happens if early structure appears again and again? What if different observations using different methods continue to point in the same direction? At that point, the issue stops being local. It stops being about one object or one measurement. It becomes about pattern. And that is where the next phase of the story begins. Once the first timing contradiction is acknowledged, it becomes increasingly difficult to set it aside, because the next observations do not resolve the tension by restoring the expected simplicity. They do the opposite. They repeat the same result. Organized structure appears early again, and then again. At first, each new case seems manageable on its own. Science is well equipped to handle unusual findings. A single early structure could be treated as an outlier. It might point to a measurement error, an uncommon local condition, or a temporary mismatch between a model and the data. These situations are familiar, and most of the time they are resolved without forcing changes to the broader framework. That is how anomalies usually behave. They appear, draw attention, and then either disappear under closer scrutiny or find explanations that preserve existing assumptions. Because of this, the initial response to early structure is cautious rather than alarmed. One example does not threaten a theory that has worked for decades. But what emerges here is not a single anomaly. As observations expand in depth and scope, early organization continues to appear. Not in one location, not through one technique, and not tied to one specific type of system. It shows up in different regions of the early universe, under different observational conditions, and through independent methods of detection. These are not repeated measurements of the same object. They are separate systems, identified independently, each one appearing earlier than the gradual timeline allows. This distinction is important. Repetition alone is not enough to establish a problem if it comes from the same source. But repetition across independent observations changes the situation. It reduces the likelihood that the results are artifacts or coincidences. Each new example stands on its own, and together they form a pattern. The gradual model predicts a very specific early universe. It should be sparse. Structure should be minimal. Any organization should be weak and statistically rare. Most matter should still be distributed broadly, without strong internal relationships. The early universe, according to this picture, should look hesitant, as though it is only beginning the long process toward complexity. Instead, what keeps appearing are systems that already show internal structure. They are not identical to what we see in the modern universe. They are not fully mature, but they are also not primitive in the way the timeline requires. They display levels of organization that imply prior development. They appear to have crossed thresholds that, according to the gradual model, should still be unreachable at that time. This creates a subtle but growing unease. Each individual example can be explained away with effort, but each explanation becomes harder to sustain when the examples accumulate. The probability that all of them are rare exceptions begins to drop. The idea that chance alone produced this pattern starts to feel strained. At some point, the question shifts. It stops being about whether something unusual happened once. It becomes about whether the early universe behaves differently than assumed. The issue is no longer localized. It begins to touch the general behavior of cosmic development during its earliest stages. What deepens the discomfort is that the pattern does not rely on extreme cases. The structures being observed are not wildly out of place. They are not so dramatic that they obviously violate known physics. Instead, they sit just beyond where the timeline says they should be. They are early, but not impossibly so, and that makes them harder to dismiss. Because if the universe were behaving in a completely unexpected way, the contradiction might be easier to recognize and confront. Here, the deviation is subtle. It accumulates quietly. Each observation pushes slightly against the same boundary. Over time, that boundary begins to feel less firm. The unease grows not because any single observation is shocking, but because the pattern is consistent. Again and again, the universe reveals organization where simplicity should still dominate. Each instance reinforces the last. each one narrows the space for coincidence. By the time several independent examples are considered together, the original assumption begins to feel increasingly fragile. Not obviously wrong, but under pressure. The idea that early complexity is rare becomes harder to defend. It starts to look less like an exception and more like a recurring condition. This is where accumulation matters most. Patterns change how evidence is interpreted. A single data point invites explanation. A sequence of data points invites re-evaluation. The weight does not come from any one observation, but from the fact that they agree with each other in the same uncomfortable way. At this stage, the gradual model has not yet failed. It still explains many aspects of cosmic evolution extremely well, but its claim about the earliest stages begins to feel incomplete. Time, which once served as the solution, starts to feel insufficient on its own. The universe appears to be organizing itself earlier and more reliably than expected. And the more examples appear, the harder it becomes to argue that this is accidental. The possibility emerges that early complexity is not a rare deviation, but a natural feature of the early universe. That realization does not arrive suddenly. It builds slowly through repetition and consistency, and it leads naturally to the next question. If early complexity keeps appearing, can the existing models be adjusted to accommodate it? Or does this accumulation point to a deeper limitation in the gradual framework itself? As these examples continue to accumulate, the usual ways of dismissing them begin to lose strength. It becomes harder to argue that each case is unique and unrelated. Harder to suggest coincidence. Harder to claim that rare initial conditions or chance alignments are responsible. Each new observation narrows the space for those explanations, not because any single one is overwhelming, but because together they form a consistent picture. What makes this especially unsettling is the independence of the evidence. These observations are not all derived from the same signal or the same method. They rely on different measurements, different analytical techniques, and different observational approaches. And yet, they converge on the same conclusion. Complexity appears early. It appears repeatedly. And it appears reliably. When independent lines of evidence point in the same direction, coincidence becomes a less convincing explanation. The gradual model depends heavily on time acting as a buffer. Time is what separates stages, what allows simple conditions to evolve slowly into more complex ones. The assumption is that organization requires long periods of growth and interaction. But each early structure compresses that buffer. With every new example, the available time shrinks. Eventually, the timeline stops functioning as an explanation and starts becoming a constraint that the observations push against. Importantly, this accumulation does not, by itself, force a dramatic reinterpretation of cosmic history. It does not immediately demand a new theory or a replacement framework. What it does instead is something quieter, but more consequential. it weakens confidence in the idea that early complexity is rare. The more often early organization appears, the less convincing it becomes to treat it as an exception. At a certain point, repeated early structure begins to look less like an anomaly and more like a condition, something the early universe may naturally allow, rather than something that must always be explained away. That shift is subtle, but it carries weight. It changes how new observations are interpreted before any equations are rewritten. This is where unease replaces surprise. The contradiction no longer feels sharp or dramatic. It becomes persistent. It does not announce itself loudly or force an immediate response. Instead, it stays present, quietly undermining the expectation of gradual formation. The assumption does not collapse, but it no longer feels secure. At this stage, the question changes again. It is no longer only about whether structure appears too early. It becomes about whether the models we rely on have enough flexibility to accommodate that fact without losing coherence. Can the gradual framework be adjusted to absorb repeated early complexity? Or does this accumulation point to a deeper limitation in how the early universe has been understood? That question does not yet have an answer, but after enough repetition, it can no longer be set aside. Once early complexity no longer looks accidental, the response is almost automatic. The gradual framework is not discarded, it is adjusted. Parameters are revisited, timelines are compressed, growth rates are increased slightly. The goal is not to change the story, but to stretch it just enough to absorb the new observations without breaking its overall shape. At first, this approach feels reasonable. If organized structures appear earlier than expected, perhaps matter clustered more efficiently under early conditions. Perhaps gravity amplified small differences faster than assumed. Perhaps early growth proceeded at a higher pace before settling into slower behavior later on. By making careful tweaks, some early observations can be brought closer to agreement with the existing models. But that sense of resolution does not last. Each adjustment that fixes one problem introduces another. Increasing early growth rates may help explain why structure appears sooner, but it disrupts predictions that worked well at later times. Compressing the early timeline can bring early observations into alignment, but it creates tension between different stages of cosmic evolution. Processes that were once neatly ordered begin to overlap in uncomfortable ways. What was previously a smooth sequence starts to feel strained. The framework becomes increasingly sensitive. Changes that once would have had minor effects now ripple outward. Small modifications produce large consequences. Relationships that were once stable require careful tuning to keep them from breaking. The model still functions, but only if its parameters are balanced precisely. Instead of a single coherent timeline, the picture begins to resemble a collection of patches. Each one is added to address a specific issue. Each one works locally, but together they reduce the sense of unity that once defined the framework. This is where frustration begins to surface, not because progress has stopped, but because every fix carries a cost. Solving one inconsistency creates another elsewhere. The more the model is adjusted to accommodate early complexity, the more it loses the internal consistency that once made it reliable. The framework does not collapse at this stage, but it no longer feels robust. It feels conditional, dependent on careful tuning rather than natural stability. And that is a different kind of problem. Because when a framework requires constant adjustment just to remain viable, the question shifts. It is no longer about finding the right parameter values. It is about whether the assumption that anchors the framework is strong enough to support what the observations are now showing. That realization sets the stage for deeper reconsideration of cosmic history itself. At this point, the effort to preserve the gradual picture begins to feel misplaced. Not because it failed once or twice, but because it keeps failing in the same way. Each attempt to stabilize the framework pushes the tension somewhere else. Each adjustment reveals another dependency, and gradually, the focus starts to move away from fixing the model and toward questioning what it was built on. The gradual assumption was never meant to carry this much weight. It was supposed to be a starting point, not a point of fragility. But after enough revisions, it becomes clear that the problem may not lie in how the model is tuned, but in the expectation that guided it from the beginning. That expectation was simple. The universe started out simple. Everything else followed from that. The long timelines, the staged development, the idea that complexity must wait its turn. But if early observations keep showing organization where simplicity was expected, then the question changes. It is no longer how complexity appeared so quickly. It is whether it was ever absent at all. This is not a conclusion. It is a reframing. Instead of asking why structure formed early, the question becomes whether the universe ever passed through a prolonged phase of near-uniform simplicity. Whether that phase was real, or whether it was inferred because it made the story easier to tell. The possibility that emerges here is uncomfortable because it runs against intuition. What if complexity is not something the universe grows into? What if it is something the universe begins with? Not in its final form, not fully developed, but already present in meaningful ways from the start. This does not mean the universe was finished early. It does not mean everything existed all at once. But it does suggest that organization may not require the long preparation we assumed. That structure may not always be the result of patience, but sometimes the condition from which evolution proceeds. This idea changes how the earlier contradictions are interpreted. The timing problem stops looking like a failure of growth and starts looking like a mismatch of expectations. The universe may not be rushing ahead of schedule. It may be following a different schedule entirely. What makes this shift difficult is that it removes a familiar anchor. If simplicity was never guaranteed, then the timeline loses one of its organizing principles. The clean separation between early and late stages becomes less clear. The beginning of cosmic history stops being a quiet, featureless starting point and becomes something more ambiguous, that ambiguity carries a different kind of discomfort. Not the frustration of a broken model, but the unease of realizing that a foundational assumption may never have been directly confirmed. That it persisted not because it was observed, but because it was convenient, intuitive, and unchallenged for a long time. Reframing the beginning does not immediately offer answers. It does not replace one clean story with another. Instead, it opens space for uncertainty. It invites the possibility that cosmic history is not a simple progression from orderless to ordered, but something more tightly compressed, more interconnected from the start. This is not about declaring that the old picture was wrong. It is about recognizing that it may have been incomplete in a way that only becomes visible now. As observations reach further back and reveal more detail, the beginning no longer looks like a blank canvas waiting for structure to appear. It looks like a starting point already shaped by organization. And once that possibility is taken seriously, the implications extend beyond any single model. They touch how we interpret everything that follows. Because if complexity was present from the beginning, then the story of cosmic history is not just about growth over time. It is about understanding what kind of beginning we were actually looking at all along. That realization does not resolve the tension. It deepens it, and it leads naturally into the final question: what it means to rethink cosmic history when the beginning itself may never have been as simple as we assumed. The room is quiet again. The slides are still open on the screen, unchanged for the moment. Tomorrow they will be shown. The language will be careful. The uncertainties will be clearly bounded. The conclusions will be framed in the way science requires, precise and restrained. There will be no final answers offered, because there are none yet. That is how it has to be. What has changed is not the commitment to understanding, but the shape of the questions themselves. The absence of a simple beginning does not invalidate inquiry. It does not mean the effort was misguided or the models were useless. It means the task is different than it once appeared. The universe may not offer the comfort of a clean starting point, and that changes what it means to explain its history. Uncertainty, in this context, is not a flaw. It is not a temporary gap waiting to be filled. It may be a permanent feature of how deeply we can look back. Not because the universe is unknowable, but because its earliest moments may not conform to the expectations we brought with us. The gradual picture gave us order. It gave us confidence. It allowed us to believe that everything unfolded patiently, one step at a time. Letting go of that picture does not mean replacing it with chaos. It means accepting that complexity may have been present earlier than we were ready to see, and that our explanations must grow to meet that reality. Tomorrow, the presentation will move forward. The data will speak for itself. The questions will be asked carefully, without drama. And the room will be filled with people who understand that not having final answers is part of the process. But tonight, in the quiet, there is space to acknowledge something else. That the beginning of the universe may never have been as simple as we imagined, and that this does not close the story. It opens it, because understanding does not always move toward certainty. Sometimes it moves toward humility, and sometimes the most honest ending is not an answer, but a question that remains.